Hi folks, last month I captured this footage of the International Space Station using my LX200 telescope. But anyone can see ISS by naked eye in the early evening or early morning sky as a bright, fast-moving object. And if you use a lunar transit, you can even capture the station's silhouette and see its structure. And with help from a friend, you can even determine its altitude, size, and velocity. Red's Rhetoric, Vincent, and myself did just that last month, capturing ISS passing over the moon during an early morning lunar transit where the station was unilluminated and a silhouette against the moon's surface. Now let's take a look at that footage in full speed. If you blink, you'll miss it, so now let's take a look at it in slow motion first with my telescope's footage, you can see here, and then with Red's Rhetoric's footage. He was positioned just over a kilometer away. Because of the distance between myself and Red, you can see that ISS took a different path over the moon. This is due to parallax. Red's footage has been aligned and sized to match mine. Now let's see it side by side. And once again, as you can see, on my images on the right, you can see that ISS is positioned differently over the moon than it is for Red's footage on the left. Now let's take a look at Vincent's footage. He was positioned just a few feet away from my telescope. You can see his images on the left, and you can see that they match the position of ISS in my images on the right. Both Red and Vincent were using P900 cameras. I was using my LX200. This image combines the pictures of the space station from Red's footage and my footage so that we can see the difference in the paths. You can even see how the path is narrower towards the bottom of the image and widens slightly up towards the top of the image. That's not a mistake. That's actually due to the space station getting slightly closer as it rises higher in the sky. The difference in the path is due to parallax, and we can use that to actually measure the range to the space station, and from that calculate things like the altitude of the space station, the size, and the velocity. Once again, the images of the space station on the right side of the moon came from my telescope. Now let's fade this to an image processed from Vincent's footage, and we can see that the path Vincent captured matches perfectly with the path I captured just a few feet away. Now, if someone was trying to trick us by flying a small drone to fool us into thinking it was the space station, they would have had to fly two drones, one over my head and one over Red's Rhetoric, in order to simulate the positions predicted for the space station for each of us. But even this would not have worked in this situation, because Vincent was just a few feet away from me, and if a small drone had been flying over the moon and tricking us into thinking it was the space station, he would have shown a significant amount of parallax compared to my images, because a drone that close to us would have a much larger amount of parallax than the space station, which is supposed to be hundreds of kilometers in altitude. Now let's take a look at Google Earth and show you where I was positioned versus where Red's Rhetoric was positioned in order to measure the distance and come up with a baseline that we can use to directly measure how far away the space station was that night. Here is a Google Earth map showing the transit center line in red. If you were standing on this line, the space station would pass directly over the middle of the moon. It's worth noting, though, that the center line will shift a bit over time. The orbital elements published for the space station were from a few hours before the actual transit occurred. We're not really trying to measure our actual distance to the center line as much as we are distance perpendicular to the path the space station took. The center line just gives us a way of measuring that. I was positioned in the parking lot on the right side of the map. Red was positioned on the walkway on the left side of the map. The green line is the direct distance between myself and Red. We tried to position ourselves as perpendicular to the center line as possible, but for logistical reasons it wasn't possible to get it perfect. For the purposes of determining our baseline, what we really want to know is what the distance is from each of us to the center line, and then add those two numbers together. First, in green, is my distance to the center line, and now in green is Red's distance to the center line. As soon as the transit was completed, I immediately shut off the telescope's tracking and allowed the moon to drift out of the field of view. This allowed me to take a picture of the background stars with a long exposure photograph a few minutes later. This allows us to have a reference point and directly measure the sizes and distances of objects in the transit video using astrometry from this image. Astrometry gives us the coordinates of every single pixel in the image, and yes, those coordinates have changed because the telescope was not tracking the sky during the few minutes between the transit and the photograph. But the timing of the transit is precisely known, and the timing of this photograph was also recorded. Because we know the exact difference in time between the lunar transit and this photograph, we can calculate what the coordinates were originally when the moon was in frame and the transit was occurring. Also, because the telescope wasn't moving between these two images, we also know the altitude and azimuth of all the coordinates in this image, because once again, we know the exact time when this photograph was taken, we know exactly where it was taken, and we can calculate the altitude and azimuth from the right ascension and declination coordinates. Here's the astrometrically solved image in SAO Image DS9. I've replaced the image data with the image of the moon, but the coordinates are originally from the star image that we just solved. The timings of the transit are in Eastern Time. If you add 5 hours, you will have Universal Time. The transit occurred on March 3rd before the time change. You can once again see that there is a small but measurable difference between the angular separation of Red's ISS path and my ISS path at the bottom of the image versus the top of the image. Let's now use the angular separation at the top of the image near the end of the ISS transit to calculate the range of ISS from us at that time. Red's Rhetoric performed similar calculations in a video he did about this transit, and for the first part we will use the same method here. If we divide the baseline of 1,119 meters by the tangent of the angle 0.125751 degrees, we come to a range of 509.8 kilometers. This spreadsheet will be in a link in the video description, and it allows us to calculate the altitude and azimuth of ISS over the horizon at the time that frame was taken, by converting the right ascension and declination to altitude and azimuth by knowing when and where the image was taken. Here's a repurposed diagram from Metabunk's curvature calculator. Knowing the range of 509.8 kilometers and multiplying that times the sine of the space station's altitude over the horizon, 53.158 degrees, we find a flat Earth altitude of the space station of about 408 kilometers. As Red's Rhetoric video points out, even if you assume the Earth is flat, ISS is still far too high to be any airplane, drone, or other aerial vehicle. But if you want to go the extra mile and determine its altitude over the round Earth, you need to find the distance of the green line, shown as visible distance here, and the red line shown as hidden distance here. This is assuming that eye level is at the horizon. For our purposes here, the height of the telescope is negligible compared to the altitude of the space station. Now, the angle at the top of the triangle, the red angle plus the green angle, is equal to about 36.84 degrees. This is also equal to the angle of the tilt shown in blue plus the angle between ISS to the observer, the latter being the green angle between the green line and the red line at the top of the triangle. Now, the tilt angle can be found by dividing the distance by 6,371 kilometers times 180 over pi to convert it to degrees. With a ground distance of about 286.7 kilometers, this comes out to a tilt angle of about 2.58 degrees, and this means the green angle is about 34.26 degrees. Now we can find the green line visible distance by taking what would be the flat Earth altitude of 408 kilometers and dividing it by the cosine of the tilt angle of 2.58 degrees. This gives us a 408.4 kilometer green line visible distance. We can approximate the red line hidden distance by using the formula r minus the square root of r squared minus d squared, where r is the radius of the Earth and d is the distance of ISS. For our purposes, we will approximate the radius of the Earth as a spherical Earth with a radius of 6,371 kilometers, and this gives us a hidden distance of 6.45 kilometers. Adding this number to the green line visible distance, we get a total ISS altitude of 414.85 kilometers. This is within 10 kilometers of the predicted altitude based on the orbit of ISS. And we can now use the ranging information to actually calculate the size and velocity of the space station as well. The astrometry indicates that the space station's apparent width is 0.0122704 degrees, and multiplying the range of 509.8 kilometers times the tangent of that angle gives us a width of 109 meters, which is exactly as wide as the space station is supposed to be. although it should be noted here that we were fortunate in that this pass was going to be very high, and therefore the station was presenting itself practically face onto us, allowing us to make that calculation very simple. Now let's calculate the space station's actual velocity. For this, we also need to know the range at the start of the transit, and you can see the angular separation at the bottom of the image. This gives us a range of 511.6 kilometers at the start of the transit. Given an average range of 510.7 kilometers and a lateral angular velocity of 0.415771 degrees and 6/10 of a second, that gives us a lateral velocity of 6.18 kilometers per second. The difference in range of 1.8 kilometers between the start of the transit and the end of the transit allows us to calculate a total vector for the velocity of the space station, and that gives us a vector of about 7 kilometers per second, which is pretty close to the expected value. So there you have it, an independent determination of the space station's altitude, size, and velocity using a simple lunar transit. Anyone can actually do these measurements using a P900 camera or similar high magnification SLR on a tripod or with a simple telescope, even without tracking capability. I want to thank Red's Rhetoric and Vincent for all of their assistance and their footage. You can check out Red's video doing similar calculations in a link in the video description. Thanks for watching. Clear skies, folks.